Okay, I think we're good to go now. So, ladies and gentlemen, welcome to the Monsoon seminar this week. As you know, our speaker this week is Mahyar Mohtadi from the University of Bremen, from the Murrum Center for Marine Geoscience Research. And he's going to be talking to us about Quaternary paleo environments and monsoons in Indonesia. So without further ado, I'm going to turn you over to his instruction. And as usual, if you want to put questions in the chat, I'll call on you at the end, or you can raise your hand and we'll deal with it at that time. But if you could keep your questions to the end, that would be great. Okay, thanks, Mahyar.
Thank you very much. I hope you can hear me and see my screen well.
Yes.
Right. So the title that was given to me was Quaternary Environmental History of Indonesia. I would have preferred Maritime Continent, which would include also Malaysia, Timor-Leste, Papua New Guinea, and obviously Northern Australia. Or even better, in the Pacific Warm Pool, which is basically the area indicated on this figure, with the orange reddish colors indicating temperatures, sea surface temperatures above 29 degrees, which give rise to deep atmospheric convection in this region. The sketch that you see here shows the two Walker circulation over the Pacific and over the Indian Ocean, but it's also home to the Northern Hemisphere and Southern Hemisphere Hadley circulations. Which makes this region very intriguing and interesting in terms of research, but also very challenging. And in the first part of my talk, I will walk you through some of these challenges, and hopefully in the second part also show some cases how these challenges can be met. I would like to thank all of those who have been contributing, collaborating with me on different papers, different studies. I'm not sure whose study I will be citing and showing here, so I'll put hopefully all of them. Certainly I've forgotten some of those. But the interesting thing is that basically all the letters are there. So if you're, not sure how I can move forward. Yeah, if your last name starts with the letters E, I, Q, or U, these are the missing letters. Please contact me. I'm really looking forward to finish this list. So anyway, so this series is about the monsoon. So we'll start with the Australian-Indonesian monsoon. A lot has been shown about this in the previous talks. So just briefly, the rainy season there is the austral summer, December, January, February, and March, where winds over the Indian Ocean are basically northwesterly or westerly, and over the Pacific are northeasterly. They carry moisture into the maritime continent and induce heavy rainfall there, which is indicated by these greenish and reddish colors here. Basically, the rain band lies right over the maritime continent and northern Australia. And in the other season, the boreal summer, is the windy season, where dry winds from Australia kind of turn around when crossing the equator, become southwesterlies and carry moisture basically to the Asian continent. Those southeasterly winds are kind of parallel or alongshore winds in southern Indonesia, south of Java, southwest of Sumatra, but also southern New Guinea. And via Ekman transport induced coastal upwelling, which is indicated here by rather greenish and yellowish colors, so relatively cooler temperatures, not as cool as in the other upwelling regions worldwide, but still cooler than normal. Whereas during the rainy season, winds, as I said before, are westerly or northwesterly, and they induce downwelling basically, and rather uniform and warm sea surface temperatures. How this monsoon evolved is basically as all the other monsoon systems based on a thermal contrast, so it's a thermal gradient, in this case between the Australian landmass and the seas further to the north of it. What you see on this panel, is the days before the onset of the monsoon, which is indicated by this vertical line, and temperatures in Kelvin. So about 2 months, 3 months before the onset of monsoon, the Australian landmass, the northern part of Australia, becomes warmer than the equator. So it kind of reverses the meridional temperature gradient and sets up a kind of thermally induced circulation and transport of low-level moist air towards Australia. However, this convection is still dry and shallow because Australia lacks high mountains, and the atmosphere in these tropical regions is rather barotropic, so hard to erode, so it needs a barotropic instability. That's what you see here. Now we are looking into the atmosphere. That's the height of the atmosphere, and these are the days before the onset of the monsoon. So there is a kind of circulation, atmospheric circulation, but it's rather shallow. And with the onset of the barotropic instability that is accomplished by the arrival of Madden-Julian oscillation, or in the years where when Madden-Julian oscillation is weak by mid-latitude troughs, that convections become deep enough to kind of maintain a monsoon-like circulation. So for the physics, that's also indicated here. So this is the Madden-Julian oscillation phase 5. That's when MJO is right over the maritime continent. And what we see here is that the heat flux out of the ocean is very high, just in the seas north of Australia, Timor Sea, and so on, Arafura Sea and Timor Sea. And another specific feature of the Australian-Indonesian monsoon is because of this land-sea contribution and because of this zonal component into this, like the MJO, it does not follow the annual march of insolation, and rather shifts abruptly from one phase, rainy phase, into the other phase. Over Indonesia, basically the southern parts, everywhere south of the equator is somewhere here. South of the equator can be regarded as the monsoon region. These are two examples from Java and the Lesser Sunda Islands, with a clear dry season, June, July, August, September, and a wet season starting somewhere in November and December and lasting until March. North of the equator, this is an example from Sumatra. There is no rainy or dry season, so by definition, these are not monsoon regions. These are deep tropics, ever wet regions like northern Borneo. And if we go further to the northeast, towards Philippines, this is the Molucca example from the Molucca Islands. Basically, the pattern of monsoon rainfall reverses. So with maximum rainfall during June, July, August, September, and that's why they, in part, are regarded to the, or is thought to belong to the East Asian monsoon rather than to Australian Indonesian monsoon. But as I mentioned before, the monsoon is not the only dominating atmosphere ocean coupled system. The other one is the El Nino Southern Oscillation. These high temperatures during normal years and during La Nina years, which is an amplification of the normal conditions, give rise to deep atmospheric convection, ascent of air, which kind of sets up the water circulation over the Pacific. And during El Nino years, as you all know, this circulation is in part reversed or weakened, and sea surface temperatures are rather cool or cooler than normal in the maritime continent. Generally, those conditions are accompanied by higher rainfall over the maritime continent during La Nina years or normal years, and the opposite during the El Nino years. However, the high resolution satellite-based measurements shows that during El Nino years, basically the large islands become wetter. Bluish colors means wetter, wetter than normal, or wetter El Nino than La Nina. And this is not because of the large-scale Walker circulation during La Nina or El Nino years. These are rather related to elevation-related moisture convergence and relative humidity. So these are because of the high mountains in Sumatra, Borneo, Papua New Guinea, and also Java and Sulawesi, those large islands experience rather wet conditions during El Niños. And this is important when we look at later on speleothemes from Borneo and Sumatra and compare them, or Sulawesi, and compare them to the one from Northern Australia. Just look at this picture and remind yourself then that those regions respond in an opposite sense to El Nino or La Nina. So the Walker circulation over the Indian Ocean and its interannual to decadal changes is called the Indian Ocean Dipole, basically the same as in the Pacific, only in the reverse sense. So warm air ascends over the Eastern Indian Ocean, over the maritime continent, and descends over the western part. And during the positive IOD years, this situation is reversed. This is because of the anomalously strong southeasterly winds during the monsoon season, so during June, July, August, September, and October. So this feature is bound to the winter monsoon in this region and is terminated by the termination of the winter monsoon. So just remind yourself, the Indian Ocean Dipole is kind of varies on interannual to decadal scale, but every several years. It's not a real cycle into this, but it occurs during the dry season over Indonesia and the maritime continent, whereas El Nino or Enzo is also an interannual feature, but it peaks during December and January, basically during the wet season over the maritime continent. So this figure kind of sums up all the difficulties with reconstructing climate from this region. If you look at the half circulation, that's basically the monsoon circulation. You have the windy season, this July, as an example, July, August, September. This is the chlorophyll A data from the satellites. And if you're working, say, on paleoproductivity reconstruction in this season, and you reconstruct paleoproductivity, and you have a high paleoproductivity signal in your record, you can relate it to a stronger, say, southeast monsoon season, but you can also relate it to a positive IOD year or season, or an El Nino year. So the signal, the pattern is really the same, somewhat stronger or weaker, but really the high productivity in this region can be a seasonal feature related to monsoon or to Enzo or to IOD. And the other way around, it could be also, if you have low productivity, it could be related to a stronger or a more dominant summer monsoon, or more negative IOD events, or more La Nina events. All these climate phenomena create or diminish marine productivity in this region, particularly in the upwelling region south of Australia, south of Indonesia. Sorry. Just a few words on ocean circulation and the Indonesian through flow. My colleagues Wolfgang Kuhn and Anne Halborn have been working on this topic a lot during the past 2 decades or so. So I'm not, and Anne has been given a talk on this in the past, so I'm not digging too much into that. Just the fact that North Equatorial Current and South Equatorial Current are basically responsible for the Western Pacific warm pool. They transfer a lot of warm tropical waters westward, and then through the Mindanao Current and North New Guinean Coastal Current. Those warm waters merge and pile up in Western Pacific. So the sea level height in the Western Pacific, sea level is about 5 to 10 meters higher in the Western Pacific side compared to the Indian Ocean side. The classical idea is that this sea level height difference triggers the Indonesian through flow, moving waters from the Western Pacific into the Indian Ocean. But another idea, another hypothesis is that's just because this is the only place where there is a leak between the two ocean basins, where actually water masses from the Pacific, currents from the Pacific can enter the Indian Ocean. That basically the ITF is just an extension of the tropical currents in the Pacific. And the reason why to think so, I will get on that in the next slide. Just briefly mention that the flow of the ITF is also related to ENSO. It's stronger during La Nina years, about 19 sphere drops, and weaker during El Nino years, about 11 sphere drops. On average, it is about 15. It's in part because of the freshwater plugs from the Sulu Sea and Java Sea kind of inhibiting the water to flow southward, but also in part because in the Pacific, El Nino causes a northward movement of the bifurcation of the NEC and SEC, and in that case, the Mindanao current weakens, and Mindanao currents actually provide about 90% of the ITF. It's 11.5 sphere drop of the total ITF. So that's also part of it relies in the Pacific itself. Anyway, and why I really favor the idea that the ITF is just an extension of the tropical currents in the Pacific is the simple fact that the subsurface flow is stronger and higher than and faster than the surface flow. These are actually modeled, but pretty close to the observations. Subsurface flow at 150 meters, it's stronger and faster than the surface flow. That cannot be explained simply by sea level height difference. But what it does, it's an example, a blow up from this region, the Hombai Strait here. The waters are transferred pretty fast in this region, especially along those channels and straits. These are 0.5 meters per second. That means that one water parcel entering the Hombai Strait leaves basically the Savo Sea within 3 days. And this is important when working with plankton community, regardless if they are plankton foraminifera or coccolithophores or diatoms, whatever. You have to be able to distinguish between local signal and remote signal transferred by the ITF. Another, I wouldn't say issue, but another feature of this region is those large shelf areas. The Sunda Shelf is about 2 million square kilometers, and the Sahel Shelf, Arafura Shelf, and Roli Shelf, that's not shown here, together nearly the same area. These are the largest shelves in tropical and subtropical regions worldwide. And these are important because if you look at the proxy-based reconstructions from this region, and this is a compilation by Jessica Rees and others from 2013, not really up to date, but it's just kind of showcase how close many of those sites are to these shelf regions. And you have to be able to isolate changes related to sea level and the proximity or the distance to land from climatically driven changes. Why is it important? This is, again, a compilation study that's Jen Wurzel's PhD thesis. I was fortunate to be the external referee of her thesis. And she did a nice job kind of reconstructing the moisture source for using the high split data for the different speleothem sites. This is, for instance, from Palawan. This is from Borneo, the famous Borneo speleothem site. This is the Flores sites. This is from Northwest Australia. This is from Sumatra, basically, and this is from Sulawesi. If we, for instance, look at this site, this speleothem site, nearly half of the total rainfall, that's the reddish color here on this, on top, on upper left corner. Nearly half of the rainfall is sourced from the Java Sea, from the Sunda Shelf, basically. And you can imagine, and this basically the entire rainfall during May, June, July until November, October, and November. So you can imagine during sea level low stand or glacial periods, this source is cut off, and this is the proximal source. It will have a significant influence on the isotopic composition of rainfall at this site. In contrast, if you go to the Sumatran side and look at the rainfall source to that speleothem, more than half of it is from the proximal sides or Eastern Indian Ocean, and even up to, I don't know, nearly 30, the other 30% of it, reddish and yellowish colors, are from the Eastern Tropical Indian Ocean. Less than 10% is coming from the South China Sea. So we would expect less change or insignificant changes in the source of rainfall on glacial interglacial timescales for this site. But another interesting feature is here, for instance, for the site northwest of Australia, during the rainy season, those are the yellowish colors, almost half of the rainfall in total annual rainfall, and basically most of the rainfall during the rainy season is coming from Southern Indian Ocean. This is a significantly different source of moisture compared to all the other speleothem sites. Anyway, so now from proxy-based issues or difficulties into the model deficiencies and limitations. When we use, or most of the models used for this region are global models, and this is one example how global models look like in this region. This model is an example, iTrace. This is the Trace 21K model with an isotope-enabled model. This is the atmospheric component of the model on top, the top 3 panels, and this is the land component. For the last glacial maximum 20,000 years ago, meltwater pulse 1A roughly, and meltwater pulse 1B, more or less. And you agree with me that all those very significant and important sills and straits and basins and islands are not resolved in these kind of models, and yeah, results in kind of deficiencies and shortcomings of models in really modeling this, simulating the climate of this region. This is an example how it looks like. This is basically a regional climate model with 27-kilometer resolution. That's a very good resolution, I would say. But what we see here is the difference to the instrumental data, to TRMM, with tropical rain data. This model unrealistically shows excessive rainfall along the mountain ranges. These are the bluish colors, higher than observed. But the ocean is underestimated. The rainfall over the ocean is underestimated in this model. These are the brownish colors. So if we increase the resolution now to 12 kilometers, the match between the simulation and the model and the observations is much better. So there is not much difference over the in terms of rainfall over the ocean, but still there is an excessive rainfall over the mountain ranges. So this is a long-standing and known issues for almost all climate models. That's elevation-related convection schemes and rainfall, which needs to be fixed. It's getting better with every generation of climate models, but still an issue. This results in kind of pre-industrial runs like this. This is basically the skill set of the models. This is a CSM 1.2 model, CMAP 5 model generation. This is the observation, rainfall over the Indo-Pacific Whirlpool on the left-hand side, and the right-hand side is the modeled rainfall. Obviously, rainfall over the ocean is much higher in this model compared to the observation. But more importantly, the islands are relatively drier compared to the ocean, whereas in reality, and as we should expect, rainfall over land over the islands is much higher than over the ocean. And also in terms of salinity, the simulated salinity is much larger in area, in extent, and much fresher than in reality. And last but not least, for those model data compilation studies, and I'm not referring from which study this figure is, not blackmailing anyone, but the issue is kind of a careful checking of the quality and eligibility of the data. Many of these are the proxy data that have been used in this study, for instance, to infer whether the last glacial maximum was saltier or fresher than today. The issue is that many of these records from the Western Indian Ocean, for instance, are on proxy carriers that occur seasonally. So it's a seasonal signal in the Western Indian Ocean. But those proxy carriers in the Eastern Indian Ocean are mean annual, more or less, or the warmer season, biased towards the warmer season. So the seasonality is an issue that needs to be taken into account. The temporal resolution of the sites, some of these sites, like here along the 90 East Ridge, basically do not resolve millennial scale climate variability. The coring technique is important if you're working on IODP or ODP cores, like here or there, or with Marion Dufresne giant piston cores. You basically don't have a very well collected, or say top few centimeters of sediment. Calibration is an issue, whether they have used the same calibrations in all these studies. You have to recalibrate the age models and all those calibrations. And the locations is also, it does also matter. If you're working on the Indian Ocean and want to reconstruct the water circulation, say over the Indian Ocean, those sites have no business being included in that compilation from the Western Pacific. Anyway, so basically, to sum up this first part of my talk, and I hope I could show you some of these difficulties, and you can take this as a take-home message if you like. There are some challenges for the proxy bed reconstructions. It's basically deciphering between Hadley and water circulation, because they leave more or less similar fingerprints, signatures in the proxy data, and between the seasonal and interannual changes, which means between monsoon and those other climate features, and respectively between seasonal and mean annual changes, so the seasonality. Unless you have archives like corals that resolve climate on say, seasonal scale, you won't be able to do that just by model or just by the proxy data. And but the disadvantage of the corals is that they are discontinuous and not reach far back in time. So we have to deal with what we have at hand. And you have to be able to decipher between local and remote signals, what is really allochthonous and transported to the site, and what is basically autochthonous and from that site. And you have to be able to isolate sea level related changes. So the proximity to land, to the shoreline, from the climate induced changes, they go mostly hand in hand. So it's not really easy to do that. So we have to have a profound knowledge of the proxies that we are using and select the proper proxy. But this is really the largest issue, the biggest issue after nearly 20 years of working in this region. I can tell that this is by far the most pressing issue that we have in this region. There are not so many calibrations of the different proxies in this region. Challenges for the model simulation, as I mentioned before, to resolve the topography, so a better resolution of the models, to solve that convective issue, higher rainfall, altitude related rainfall, and basically check the quality and eligibility of the data when comparing with the data. To just showcase one of these issues that I mentioned here. I'm showing you two records offshore the Sunda Strait. These are the blue and red stars. The blue one, these are the SST records of those two sites. The blue one goes back to stage 8, so the last 300,000 years. This is the alkanon-based SST reconstruction of that core, and the magnesium-calcium-based SST reconstruction of the same core. And the red one, again, the same two parameters going back to stage 6, say 140,000 years ago. They do match nicely also in terms of the absolute value. They are all plotted on the same axis. So make us confident in what we have measured. And they show some similarity to the insolation and precision over the last 300,000 years, and also to the sea level changes as indicated by benthic stack, global benthic stack. In terms of, but they show also some differences. There are differences between the alkanon-based SST and magnesium-calcium-based SST, and we have been looking into this. PhD students back then in 2014, he was looking at the core top, basically surface sediments in this region, which were mostly dated. So we were confident that they are post-bomb and can be compared to the instrumental data. So the alkanon-based temperature reconstruction from these core tops matched, particularly in the Monsoon region over South Indonesia, much better to the Southeast monsoon temperatures. Those are the yellowish and whitish colors showing almost no difference to the instrumental records, except for those two sites, but those two sites are not modern. We think that they are not modern. So our inference back then was that the alkanons in this region reflect the June, July, August, September temperatures, if you like, until we studied a sediment trap from the same upwelling region, south of Java, going from December 2001, now in this case, to December 2002. In yellow, you see the satellite-based temperature, so the Advanced Very High Resolution Radiometer in green, showing the upwelling, the onset of upwelling during June, July, and peaking during September. So this is the upwelling season. As we expected, the alkanon concentration and fluxes were highest during the upwelling season, during the same season, so far so good. But if you look at the alkanon temperatures, UK prime 37 and text 86 records, they do not show any similarity with the temperature SST evolution over the same period. So kind of throwing us back to square one in identifying what we are basically looking at when we look at the, say, alkanon or text-based temperature reconstructions. Okay, so far so good. Now let's get back to the rainfall proxy data. And what I'm showing here are, again, those Paleocene records, 5 of them, different color coding refer to the same site. So the red curve here refers to the Borneo Paleocene, and the brown one to the Sumatra, and so forth and so forth. Only over the last 10,000 years. Why the last 10,000 years? Because then we can neglect the sea level effect. By 10,000 years ago, all those shelf areas should have been flooded. So there is not much change in the rainfall source. So we will be probably looking at the changes in the rainfall, isotopic composition of rainfall. And from this data, it seems like the record in Borneo show a peak humidity or wet period, upward means wet, during the mid-Holocene, similar to the record from Sumatra, and also the record from Northwest Australia. Whereas those in between, and this is a lake record, it's not a Paleocene record from Tuvuti, Lake Tuvuti in Sulawesi. But similar to the Flores Paleocene data, they show actually drier conditions, relatively drier conditions during the same period. And interpreting this pattern might lead you arguing that the Indo-Pacific whirlpool was larger during the mid-Holocene, so the northernmost and southernmost extent of the whirlpool were wetter. So, and in turn, so the area in between received less rainfall. You can also argue that the IGCC migration, the amplitude of its migration was larger, so further to the south and further to the north. Some of these records have been interpreted in terms of ENSO, like this one. So insolation maximum, September insolation was at maximum during the mid-Holocene. So the interpretation of this record was that maximum September insolation at the equator may kind of stabilize the conditions in equatorial Pacific. So more La Nina-like conditions in this region. Well, we just saw at the beginning that it's not really easy in terms of rainfall over Borneo and its relationship to El Nino or La Nina. And some of them have been related to Indian Ocean dipole, like the last 2,000, 3,000 years of this record. So you can have a variety of options to choose from what the cause of rainfall changes at your site is, especially when your site, like the Speleothem sites, records basically an average of several years. Now, let's look at the different parameters. That the titanium to calcium ratio, that's a parameter that has been related to terrigenous runoff. Titanium comes mainly from land, and calcium is rather produced in the water. So the ratio tells something about the runoff that can be related to rainfall. So upward tier against means weather conditions. Those sites along Sumatra suggest an increase in rainfall north of the equator that kinds of dips and tilts and changes to exactly the opposite towards south. Somewhat with an insulation, such as an insulation controlled runoff. But if we now move further to the east, to the real monsoonal Indonesia, this is the site that you just saw in the previous slide. Now the three records further to the east of it in the Lesser Sunda Island, they don't show any insulation pattern, but show just increasing runoff titanium to calcium ratio during the late Holocene. So really, depending on what parameter you're looking at, you might end up with a totally different and inconsistent outcome of your data and eventually your interpretation. What about sea surface temperatures? This is a compilation again by Paula Mafos-Sanchez and others in 2019. What we did then, compiling all the SST records from the West Indo-Pacific whirlpool. What we found then is that the northern part of the Indo-Pacific whirlpool during the Holocene did not experience any change in the SST. The SST is rather flat. If you look at the last 10,000 years, these are from, we called it Northern Hemisphere, or from Sumatra, or from South China Sea. But the more southern sites from the Papua New Guinea or along the ITF path or in the Timor Sea show a kind of 1 degree cooling over the course of the Holocene. 1 year later, Hao and Deng and others did the same sort of compilation, now excluding the South China Sea and Eastern Indian Ocean sites. These are the sites that were included in this study, and the SST there shows a more subtle decrease, but the stacked SST also shows a kind of 0.5 degree cooling over the course of the Holocene, similar to what Brad Lindsley and others found basically 10 years ago. So we can confidently say that the SST in this region, at least south of the equator, have decreased by 0.5 to 1 degree during the course of the Holocene. Thermocline story is rather different. Again, that's the same study by Hao and Deng and others. There are 2 types of thermocline temperature evolution over the Holocene, one peaking at about 10,000 years ago, and the others kind of remaining high and peaking basically during the mid-Holocene, about 5,000 to 6,000 years ago. We argued that the early Holocene peak using a CSM model is related to precision, so minimum precision back then, this is a model that is forced only by orbital insolation and greenhouse gases. This is the response to precession during the early Holocene at thermocline depth, 120 meters. So the whole Western Pacific, particularly the Southern Pacific, is warm. This is actually a cross-section into the ocean, so the upper 200 meters or so. 30 degrees south of the equator and 30 degrees north of the equator. So this warming is really in the Southern Pacific. So precession was responsible, according to this study, for warmer thermocline temperatures during the early Holocene. And for the mid-Holocene, that September insolation maximum, which is again shown here, same model, same depth, 120 meter, showing warmer thermocline temperatures in the whole Western Pacific. So now, going further back in time now on glacial interglacial scale, there is a proxy that is commonly used. That's many of my own studies involved in this, and I could go on and show some other delta H&O of seawater from the Western Pacific, which I didn't do here for whatever reason. But they basically all show no change on glacial interglacial scale. So the glacial values are similar to the interglacial values, like in this core and this core, only offshore Sunda Strait, and this is probably because of the opening of the Sunda Strait and the intrusion of the fresher Java sea waters into these sites. There is a change at about 10,000 years ago when the Sunda Strait was open. But again, also here in the South Sea, there is no significant change, all within the area on glacial interglacial scale. So this delta ocean of seawater is rather reflecting a large-scale hydrological cycle than rainfall. But the fact that there's no glacial interglacial change in these records is intriguing, and that the kind of abrupt climate changes in the northern hemisphere or North Atlantic, like Heinrich Stadios and Younger Dryas, are more pronounced, as you see here, or here, or here, than the glacial interglacial changes, is also very intriguing. There has been some models supporting this. This is what we showed, that basically that the seesaw pattern during the Heinrich, when northern hemisphere cools and southern hemisphere warms, and basically the whole monsoonal region in South Asia and west of maritime continent experienced drier conditions during the boreal summer, which were related back then to Rossby wave-like teleconnection, creating a kind of clockwise circulation over the Indian subcontinent, creating down a descent, basically atmospheric descent and drier conditions there. Right or wrong, these are, I'm not touching much on these abrupt climate changes, just going back to the glacial interglacial variability. So the LGM, the last glacial maximum, looks like this in most of the models. These are 12 models, the PMIP3 models, that's the older generation of the models, showing for the maritime continent, basically drier conditions during glacial periods, last glacial maximum in this case, regardless if you look at the mean annual conditions, December, January, February, or June, July, August, September, so the different monsoon systems. And this is simply because of the exposure of the shelves in the models. Whenever you turn water to land, it becomes dry. The same generation of models, however, suggests that this is one example, that the area of ascent has not changed, has not moved from this region. Basically, the RTCZ, or the rain band, if you like, lies still over the maritime continent in those exercises. So the amount of moisture in the atmosphere should be less. That's what the models suggest. What do the data suggest? These are thermocline and surface temperature reconstructions from along the ITF path, and also from the South China Sea by Xu and others more than 10 years ago. and they looked at SST and thermocline evolution during the last glacial, or time slices during the last glacial maximum during the early Holocene and late Holocene. And they inferred that the thermocline shoaled from LGM to early Holocene, and they related it to the intensification of the ITF. That is probably, most probably true, but we see also this showing in regions that have no business with the ITF, like here west of Sumatra. Also there, basically the thermocline is deeper during glacial. These are the open symbols here, and are shallower during the late Holocene. So we see also a shoaling of thermocline also in regions unconnected to the ITF. And basically a deeper thermocline during the last glacial maximum actually suggests a stronger convection. So what we did then, we tried to work with as many parameters as possible. This is one example from a core from Monsoon, Indonesia. We measured whatever we could, and organic and inorganic parameters. These are and came up with the idea that basically the wet season was wetter and the dry season was drier. So the wet season, these are the deuterium records from that side, show wetter conditions during the last glacial maximum. That's this yellowish bar here. But our proxies of fire and fire intensity, together with the pollen data, suggest that the dry season was drier. This axis is flipped. So the LGM during the dry season was drier, similar to the finding back in 2014, suggesting that the dry season was drier. It was a site from the South Sea during the last glacial maximum compared to today. So, and the same generation of models that produce a dry last glacial maximum, regardless if you look at the different season or to the mean annual, if you take the same models, that's a multi-model experiment, but a different study, you can come up with the same results as a proxy data with a drier winter and a wetter summer, similar to what we find in our proxy-based records. Different or in part similar processes that lead into this, but by now our state-of-the-art understanding of the monsoon of Indonesia is a stronger seasonality during the last glacial maximum, which is not really related to the changes in the insolation in part, but not completely controlled by insolation changes. And this is simply because of those regional character of this system. This is also shown this stronger seasonality or the stronger interannual variability during the last glacial maximum by the study by Thermocline and others in 2019. This is a comparison of the LGM single foraminifera measurements in blue compared to late Holocene single foraminifera measurements in orange. And we see that at these sites during the LGM, the range of those measurements is larger than during the early Holocene. And the conclusion from this study was that the LGM climate was more variable than the late Holocene. Of course, it was again backed by the CSM model, showing an El Nino-like pattern in the Indian Ocean, which is not really El Nino-like because in the Indian Ocean, it's reversed basically. That's a kind of amplification of the normal state during the last glacial maximum. And in order to confuse you completely, at the same year, another study using kind of similar set of data, partly the same sites even, by Jeroen Groneveld and others, showed that actually the individual forum analysis does not reflect climate variability in total. So not a one-to-one, that would be this line, change in the different parameters, if you look at the magnesium to calcium ratio or the delta O18, as it should be expected. There are some sites that are completely off and some species that are completely off. And the inference was that basically the forums adapt their habitats and seasonality to changing climate in part, and kind of do not reflect climate conditions one-to-one. And I'd like to finish my talk with this figure is again a modeling, the same model that I've shown before. That's the iTrace model. Now showing changes in the amount of rainfall as modeled, as simulated in blue, and in the isotopic composition of rainfall shown in red for different sites. Some sites, as we discussed before, like Sumatra and Java, show the same kind of change in the isotopic composition of rainfall and the amount of rainfall. So the sign of change is the same simply because probably the source of rainfall has not changed much on glacial interglacial timescales. But there are sites closer to the sun, to those large shelf areas like here, that show exactly the opposite sign of change. And suggest that we should be cautious with the isotopic composition of rainfall when we reconstruct rainfall amount at these sites. Regardless, all of these sites show a very strong response to sea level changes. That's at about 14,000 years. That is prominent in all of these sites. So sea level remains a big player in this region when we go back in time. So I will leave you with this, and thank you very much for your attention. I'm happy to take your questions.
Thank you, Mahyar. Thank you very much. While we gather our thoughts here, I was wondering myself, if I might ask a little question here. In some ways, it seemed a little bit confusing. I mean, perhaps it reflects just the very great size of Indonesia, that some areas were seeing more South Asian monsoon and water coming from the Indian Ocean, and some from the Pacific. And I wondered to what extent you felt that the climate in this region, it almost felt like it was being buffeted between these big systems, the dipoles and various monsoons. But do you think that this region might also be affecting these other areas, like things like the strength of the Indonesian through flow? Could that be affecting the South Asian monsoon, or is Indonesia just one big victim, climate victim, if you like?
Very good question. It's a yes and no. If you look at the models, depending how you run the model, you get the result that you like. If you basically run the housing experiments for the abrupt climate changes, say 100 events and so on, so, because the forcing is in the North Atlantic. And that's our understanding of how the forcing works during 100 schedules. So you get the response. So the tropical region is only responding to the forcing in the northern high latitudes. If you run the model simply by insolation, then you find features in the tropics that might be forcing the climate, like a warmer thermocline, as we saw for the early Holocene, warmer thermocline in the Pacific or in the tropical Pacific. This area certainly affects climate worldwide. That's basically regarded as the engine of the modern day atmospheric circulation. So certainly changes in the temperature and the convection in this region has a global impact, but that's a chicken and egg problem that you can solve only with models. And basically that's also based on how you set up your model. We have been doing different set of experiments. Xiaojun Wu did it basically to be fair, running those I-trace models, different models using different forcing. I don't find the proper slide for it, but with just ice volume changes, what different sensitivity runs, like only insolation and greenhouse gas, and then adding up sea level changes, adding up what was the other one? ITF and so on, and looking at the responses. And what she found was that the largest response is to sea level, basically, and on those timescales that she was looking at. And all the other forcing had little or generated little response compared to the sea level.
Thank you. Does anyone else have a question? Ah, no? Yes, Jerome. You have to unmute yourself, mate.
Okay.
You're still muted.
I'm unmuted now, right?
Yes.
Yeah, okay. With all these different model experiments, do you know of if there's anything running on biogeochemical models already which are predicting how the proxies are being generated during different seasons? So if we can predict, for example,
if I really want to understand the proxies, I would go and do some field studies instead of relying on some models. I know that has been done elsewhere, but what we, as I mentioned in my talk, the most pressing issue is that we do not know much about the seasonality of these proxies, the depth, habitat depth of those plankton communities. Is a heterogeneous runoff indicator that we are using, titanium calcium, really reflecting rainfall amount? Are those speleothem sites, the delta 18 of calcite, really reflecting the rainfall amount? We know it, but there are some observations for the Borneo site, for instance, and for the Flores site, and they show that is, say, in part related to ENSO, in part related to diurnal cycle, and so on. It makes things more complicated, but in my understanding, the only way forward is basically monitoring over several years all these different proxies. For the marine proxy records, what we are lacking really are sediment traps. There is only one sediment trap from this whole region. There's only one sediment trap offshore Java. It's ran for 2.5 years, and only basically 2 years of those 2.5 years were usable. We have only 2 years of sediment trap data where we can say something about the seasonality of those proxies. We certainly don't have any tow data collecting in situ data during different seasons and different years. That kind of complicates our understanding. Well, you can argue and say this is the issue everywhere in the world, but particularly in this region where you have to have a good understanding of how your proxy works, it's not as simple, say, as let's say in the Nordic seas, where you have ice cover in half of the year, and the other half of the year you don't have an ice cover. This basically a B system. Here you have A, B, C, D, E, F system, and you have to really monitor those proxies over several years, several ENSO years, several IOD years, several monsoon flavors, in order to understand how they record those climates.
So in that sense, it may actually be very helpful to have models, maybe even a regional model, which is predicting, for example, for forums, how they would respond if you go into an El Nino year or an IOD year, because we know that we're probably not going to have those very long sediment traps hanging around in the Indonesian area.
Yes. I mean, if you're pragmatic, you will start working with the models first, and then you set up a project to go into Indonesian seas and collect field data. Sure, but still, regional models, as far as I know, and discuss with the model community, don't do a really good work. Just increasing, as I also showed, it increasing the resolution of the models, or just being a regional model, is not kind of a recipe to success. Yeah, put it simple, the complexity of the system is not captured by any model yet. And until we don't have it, results could be also misleading rather than helping.
I see that Pallavi makes a comment in the chat. I don't know whether she wants to say it herself, but about proxies at various places may or may not reflect the climate, as mentioned.
Yeah, sure. Completely agree. That's basically what also Jeroen showed in his study, course of study.
Yeah. Thanks, Mahyar. That was great talk. I also wanted to add one thing, as you mentioned about set traps, is that if we were to reconstruct in any part of the world climate, then probably we need regional long-term time series of sediment traps, ideally, right? Because if proxies do not really capture the climate, then clearly you need site-specific, if you like, or region-specific set traps to really capture whether you have same dynamics, like, for example, taking foraminifera. So whether at a location, a particular species or a series of species do capture the behavior that we would expect it to capture. So, particularly in a very dynamic place like Northern Bay of Bengal, for example, and places like that, where, the changes in runoff as well as wind pattern might change back in time, for example. Okay, so if that happens, and if you don't have a clue how that might reflect, I mean, particularly for the modern, we may not even have an ideal scenario. Basically, modern may not even capture some of those extreme past climate that we might end up seeing in the proxy record back in maybe
I agree totally, and the results that I was presenting, they were from the southward side of what was in the Pacific War,
going back in time. So I think.
Oh, sorry. Go ahead.
Yeah, no, I completely agree. So there are lots of a layer of problems or layer of challenges, I would say, right? So of course we have to start somewhere. So whatever we have to work with it. But I don't know, how do we go about actually having a proposition, I don't know, from the community that we need at least time series of these set traps to really understand what are we looking at, what signal we are looking at in climate record, even from
the issue
for some locations.
The issue is set traps are expensive because of the ship time.
Of course, I know that.
And not very popular because the outcome is usually not in Nature or Science publication, but just somewhere.
Of course.
So it's hard to get them really through the funding agencies. But I agree totally. So we need those time series in order to better understand our proxies. And again, the results that are shown here are from the simpler part of the Western Pacific world. The part that Anne and Wolfgang have been working on for years is much more complicated. So I basically didn't touch that area in this talk because I mean, we had that instant program. There were several years of monitoring, at least 3 years, I think, of monitoring, 3 or 4 years of monitoring the physical properties of water masses along the different straits in the maritime continent. But at those mooring sites were no sediment trap connected, so we don't have any proxy monitoring from those sites.
Well, thank you very much, Mahyar. So I think we should probably wrap things up for this week. I just want to remind you that next week, our speaker will be Cristiano Chies, who's going to talk about millennial scale changes in the tropical South American precipitation. So change of hemisphere. It'll be at the other time, of course, and you will be getting an email from me about that. If you're signed up for the list, if you're not, send me an email and I will add you to the distribution list. But in the meantime, let's thank Mahyar for his splendid performance this morning.
Thank you very much.
Thank you. Thank you. And see you all soon, I hope. Stay safe.